So thank you everyone for attending today. I will be presenting the Food and Agriculture's organization's hand-in-hand geospatial platform. So let me start with a recap on the hand-in-hand initiative for those of you that are not familiar with it. So the objective is to... The objective is to identify and actualize the biggest opportunities to raise the income and reduce the inequalities and vulnerabilities of the rural populations. So that's the big ticket item for the hand-in-hand initiative. The approach is to improve targeting and tailoring of policy interventions, drive innovation, encourage finance and investment flow, and institutional reforms. The hand-in-hand initiative is evidence-based, country-led, and country-owned. So this is an overview of the process that we undertake with the hand-in-hand. So it all starts with an agreement between the country and FAO to work together on the hand-in-hand initiative and a handshake. Immediately after that, we set up a country team with the right skill set that will support the needs of the country. Ouch. Okay, so once we have the country team set up, then we can move directly on to the dialogue with the government. So during this phase, the analysis is undertaken on the value chains that have been identified by the government as being priority. And the key point here is that we want the investment proposals to be driven by evidence. And so there's a lot of toing and froing and a lot of analysis, which I'll be talking a bit more about in my presentation this afternoon. So once we have this analysis package, it then gets passed on to the executive roundtable. So during the executive roundtable, then the decisions are made on the actual interventions that the government would like to pursue. So there's a ranking and an evaluation of those proposals. Once we have a list of investment opportunities, we can proceed to the next point, which is a more detailed investment opportunity. With these investment opportunity packages, we're able to take those to donors, including financial institutions and private sector, in order to match the interest in donating to the requirements within the country. And people can be very secure in these proposals because they know that they've been driven by an evidence-based mechanism. Finally, once we have successfully identified a match, then we proceed to the implementation and the monitoring and the evaluation. So that was a very short recap of the hand-in-hand initiative. So in step dialogue with the government, I talked about a lot of analysis packages. So let me talk about two of the techniques that we use. The first technique we call agricultural typologies. So this is really about identifying the area with the greatest investment opportunities. We start with three baseline maps. So on the far left, we have the agricultural potential. So that will be for a specific value chain. In the next one along is the economic status of the people living in that area. And then we have the technical efficiency for the value chain. So we have these three base maps. They are then combined together in what we call the agricultural typology, which is essentially a ranking of which areas or which districts we would like to investigate further. So that's the brightly colored map that you see in red and green. So in the very light green, you'll see areas that are being identified as being already high performance. So the investment opportunities and the return would be very limited in those areas. In the red, you have the areas that are being identified as having a moderate agricultural opportunity or some other issue that prevents the development within that area. So the sweet spots is this dark green in the middle. So these are areas with high potential and high priority within the country. Again, these maps are developed with the country, with support from FAO, and they're refined. So how do we calculate the maps? So we take the socioeconomic data, so that's mostly things like the household surveys and many other kinds of inputs also. And they are summarized by the district level that we're working at within the country. And then we also take base geographic data. Again, the base geographic data is summarized by the districts. And then the economists then run a stochastic frontier analysis that produces the two of the three maps that we use as the baseline. That's the agricultural potential and the technical efficiency. Finally, we identify a good source for the economic status maps. So we have various sources that we use in different situations. And then the three of them are combined to give us this agricultural typology. So some examples of the input layers that we use in this analysis, and it really does depend on the value chain that we're looking at, include things like the land cover, the access to markets and the population locations, so the distance to the market, the distance to a port for export or an airport. Then we also take into account the infrastructure. So, for example, the mobile phone coverage or the access to electricity. And then, of course, the asset wealth index. So putting these three maps together, we end up with these typologies. So these are just two examples that I have on the screen today. The first one is for crops on the left-hand side, and on the right-hand side, we see one that refers to livestock. So the difference will have been in the input data sets that we use in this analysis. So some of the data sets would be the same. Okay, so at this point now, we have identified for the value chain which areas are a priority. And it's not just because we particularly like the district, we have this body of evidence behind it that justifies the choice of working in those areas. So the second tool that we use in the hand-in-hand initiative for analysis is a suitability analysis to identify top locations. So this is a multi-criteria decision analysis for those of you that are familiar with the technique. And today I'm going to talk about one concrete example, which is where we would like to build crop storage locations for rice. So we take many layers of data, and the data is then normalized and standardized so that we can directly perform calculations on it. So an example here is that we're taking the production potential of rice, the production of rice, not the potential, the population density in terms of human resource, the port accessibility map, the major cities, and the distance to regional cities. So the individual factors and the layers that are chosen will depend on the particular value chain that we are trying to investigate further. So then we summarize all that in a heat map. So here we see a map with the shades of blue that represent a darker blue is showing an area that we consider to be a more appropriate place to be building these crop storage locations. We now take that map and then we summarize it, or we threshold it to identify the hotspots or the 99th percentile where we would like to investigate further. So once we have the areas we'd like to work in further, we then apply some constraints to those areas that we're working in. So one of the constraints here, for example, is the access to financial institutions. So we take the distance to a bank, 10-kilometer distance, and the access to major roads, and we use that to clip the original top locations. We also clip the map based on some key infrastructure that's required. So we saw earlier, perhaps we need mobile phone access or electricity or some other fundamental input. So now we've identified these areas for further field validation, and at this point, field visits are conducted and assessments to identify those specific points. So we've ended up with an overall heat map, a highly suitable area, and some individual locations where we're planning to build this infrastructure. So in this case, we ended up choosing 7 sites that we were proposing to make this investment. Okay, so that is a summary of the hand-in-hand process and how it relates to the agricultural analysis that we undertake to support the evidence-based approach. So now I'd like to switch to a different topic, which is the platform itself. So in FAO, we have built the agroinformatics platform, and the agroinformatics platform underpins the hand-in-hand geospatial platform and many other applications that we will be seeing later in this presentation. So the purpose of the platform is for decision support, the design of interventions, monitoring and evaluation. The characteristics that we're striving to have in the platform are that the data is trustable, multi-sectorial, interoperable, standards-based, and driven by metadata. The platform also allows the ability to search, share, and perform basic analysis. So in terms of the data that we've assembled within the platform, we've taken it from various units within FAO, from space agencies, NGOs and governmental partners. We're currently covering as the key channels soil, land, water, climate, fisheries, livestock, crops, forestry, trade, social economics, and many other areas, as you will see shortly. So we have a few mantra that are driving our approach, that the data should that we should ensure that those authorized can find and consume accurate and up-to-date and convenient data, that we have the data in a unified catalog that organizes, unifies, and integrates data to create a holistic view and reduce fragmentation and duplication. So especially within the organization, we were seeing that many data sets are processed by many different groups, and that there are economies of scale in performing this once in such a way that the data can be used for many applications. The other mantra we have is that the data is well documented. So here we're talking about describing the data, tracking the data, its associated digital rights, its provenance, its usage and copyright, and the qualifications on where the data should be used or shouldn't be used, or what you need to be careful about. We also try to ensure that the data is standardized in such a way that we're able to perform analytics across data sets that previously was not possible. So we're taking data perhaps from 2 completely different areas. Maybe we're taking fisheries data together with some other data set that wouldn't normally be very convenient to work together. We're making that happen through this platform. So the website itself is built on an open source product called Terra.js out of Australia from Data61, which is part of their desire to improve the accessibility of data. It was a platform that we selected and extended. It works directly in a web browser. There is no need to install any special extensions. It's mobile friendly, so it works mostly on a mobile phone. There are 1 or 2 functions, some of the analysis functions that don't, but on the whole, everything works very smoothly on a mobile phone. And so that's the approach we take for the application. And we see a screenshot here of it showing on my phone. So within the platform, we have a catalog. So we have different applications. Here we're looking at the hand-in-hand geospatial platform. And you'll see that highlighted in towards the middle of the screen, we have crops and vegetation. So we consider that a channel within the application hand in hand. And then within a channel, we have data that is organized by different topic areas. So here we have, for example, production yield and area harvested, maybe the agricultural stress index. In this particular section, you'll find information related to crops and vegetation. And in the right-hand panel, we have a snippet from the metadata record that accompanies the data. So the platform out of the box, we include many areas of interest. So when you're doing analysis, often you would like to perform the analysis on a well-known area. So we support hydrological subbasins, we support fish catch areas, subnational boundaries, sometimes down to village levels. And so those are available as built-in standard concepts within the platform. It's also possible to upload your own shapes or to draw shapes directly on the map for performing analysis. So let me talk about some of the different kinds of data that are in the platform with some concrete examples. So the first example I'm showing today is from FAO's flagship FAOstat database. So this database is mostly an annual national time series. So through the platform, we're able to link to the FAOstat database and perform a query. And without any geospatial knowledge, we're able to use the coding system, so these well-known coding systems. So in this case, it's M49, for those of you that are familiar with the national coding system. And the map is automatically rendered. So here we're looking at the live animals, and we can switch between cattle and some other live animal, and the map will follow us. We can also change through time, and again, the map will follow us. So it's been very easy to integrate a data set that previously was not geospatially enabled. If we click on a country, we get a spark chart because this particular data set supports time. So here we see the evolution in Angola. And we can pop that out and add it into a chart for future comparison. So now if I was to pick another country, so let's say I click on, where did I click here? Can't see. Tanzania, sorry. So here we click on Tanzania. Again, we see a spark chart, and I can add it to the chart at the bottom. And now I can start to compare this tabular data for the same variable in two different locations. And I can proceed to add a different country. So in this case, I'm adding Zimbabwe. And also, we're able to zoom in. We're able to zoom in on the chart and then download the chart either as a picture for inclusion in a PowerPoint or the actual data that is backing that chart. Okay, let me talk about a slightly different kind of tabular data. So any data sets that returns from a query, a latitude or a longitude, or some other way that we're able to uniquely identify the point location, we can render as a point. So I've chosen here as an example to demonstrate today FAO's reference database for animal disease outbreaks. So here we're filtering by Rift Valley fever, confirmed events between 2020 and 2023 for all countries. So the map is rendered here where there's, I think you can probably see Uganda, there's this big blue marker on it. So if you click on the point, this is for a specific date. So we're looking at the 18th of March, 2023. You can see that there is details about that outbreak event. And indeed, there's a deep link into FAO's reference system for animal disease events. So if you were to click on that link, it will open the Empress Eye, which is the name of that system, giving you the whole record of that animal disease event. We're also able to step through time as we were able to step through time with the national data sets. So we can either use the time selector underneath the filters on the left-hand side, or if you look carefully, hopefully you can see at the very bottom this timeline. So you can click on the timeline or indeed play it as a video. And as you change the timeline, the position of the dots on the screen will change. Finally, maybe we want to turn time off and just see all of the events that happened within that time period. So here I've elected just to show all of the points that meet that criteria in one go, regardless of the exact dates on when those outbreaks happened. So both with the tabular data we saw from FAO stats, so those coloring the polygons, and the latitude and longitude point data, they are backed up by a table. So we're able to see the table of the data that is displayed on the map, and we're able to then show the map at the same time and filter the map on the table. So in this case, what I've chosen to do is to filter the data, in this case by the species, and I'm only showing the outbreaks that occurred in domestic sheep. So this is a way of using the table to filter the contents of the data shown on the map. We can also take the table and do some pivot table analysis. So here we're pivoting that data to summarize it. So we're summarizing it, I think I've chosen country by animal species. So you see, I immediately get these totals that are a breakdown and a summary of that particular pivot table. And then I can apply a style to that table. So in this case, I'm going to choose a table color heat map. So now the higher values will pop out of the table. So the table itself can also be downloaded so that you can use it in a spreadsheet. It downloads as a spreadsheet for future use. Okay, so let me move on to some more traditional data. We also support many different kinds of geospatial data, including vector data and raster data. So what we're seeing on the screen here is two different data sets coming from different, completely different groups. In fact, on the left-hand side, we see the gridded livestock of the world, which is an FAO product showing the likely distribution of animal densities. So I've chosen to show cattle here. So the red on the left-hand side is showing the cattle densities. And then on the right-hand side, we're showing the world pop data set, so not from FAO, which is showing the population densities. So we can very quickly compare where these cattle are and where the humans are. So coming back to my earlier example of Rift Valley fever, if we put those disease events on the map, so Rift Valley fever is transmitted by a mosquito. The mosquito can infect both humans and cattle. So now we can very quickly put these three data sets together. I can see where the people are, I can see where the cattle are, and I can also see where these outbreaks are. So this is an example of how we can take data sets from very different sources and quickly compare it over space and time. Because if I change the time horizon, then the data will follow it, so the outbreak data and the population data. So we can also do the side-by-side comparison of an individual data set. So I've just chosen one from the WAPO, the Water Productivity Portal from FAO. So they have many very detailed data sets that are part of the platform. So here we're looking at the transpiration, so it's a 30-meter data sets from the Bekaa Valley. And you can see that I've taken the data set and I've duplicated it. So it's exactly the same data, but on the left-hand side, we have 2022. On the right-hand side, we have the same decade. This is 10 daily data in 2023. So we can quickly do a comparison of the same data set between two different time periods. This equally works for other kinds of raster data sets. So here we're looking at, for example, the climate anomalies, in fact, sorry, the precipitation anomaly specifically here. It's a monthly anomaly. And this is a data set that we have integrated from CHIRPS. So we can see the areas where it was wetter or drier for this specific month on the left-hand side. On the right-hand side, I've chosen to put the future forecast, monthly forecast for the anomaly. So here we can very quickly see if it's dry and it's expected to be continue to be dry, then we can see them together very quickly in the same map. So earlier in the presentation, I talked about some of the well-known areas. So an example of a well-known area here is Lamwo, which is in Uganda. And so by putting the layer on the map for the districts, we're able to select it. So this black ring that you see up there is this particular district that I'm interested in. So we can send that information over to the back-end analysis services, and then they will summarize the information for that particular well-known area. So the chart at the bottom is showing the long-term extremes in gray, so the highest and the lowest point ever calculated over that whole time series. I forget how far back this one is, maybe it's to 1960. And then we also have the long-term average for each month. And then we have the last complete year and the evolution of the current year. So that very quickly allows you to see how the current season is progressing and make some quick assessment on that particular area. So another kind of analysis we support is what we call categorical analysis. So in this case, the pixels in the raster image don't represent an absolute value, but they represent a class. More specifically, this is a land cover classification. So here I've drawn an area on the map, and then I've sent it to the back-end analysis functions, and then they have returned this pie chart that is showing me the proportions of the land in that area that fall into the different land cover classifications. So in this case, you can see it's mostly different kinds of tree cover in the area that I chose as the example. So when the data is detailed enough, we can go right the way down to doing field level analysis. So some of the data sets we have do go down to 10 meters. This particular one is a 30-meter data set. And here we're looking at the net primary product, which is a 10-daily image. And we can see along the bottom a comparison of two fields directly within the system. Again, because the result of that analysis is a table in nature, we can also see the data in the table and perform the same kinds of features that I talked about earlier when I showed you the table function. So we can filter for when the transpiration was above 100, for example. Another kind of function that we have built into the system is to integrate with the various models. So within FAO, we have many different models undertaking different kinds of analysis. The example I've chosen here is coming from CPAL, which is in our forestry department. And it's able to calculate raster-based answers to a complex set of questions. So here the user interface provides people with a set of guided questions. Based on the answers to that questions, we post that to the analysis service, in this case CPAL, choosing which analytical function I would like, and it returns a raster image that is then displayed on the map. Once I have the raster image, then I'm able to then download it and take action on it. So many of the data sets we have are very big, so they can be very expensive to download and very inconvenient, especially if you don't have such a good internet connection. So we offer the ability for not all data, but a lot of data, to be able to crop and export that. Again, we can use the well-known areas, or we can simply draw on the map. So here I'm drawing an area on a map that I'm interested in, and then I click the export, and then I'm able to see that map directly in QGIS and perform some offline analysis. How am I doing for time? I'm running out of time. Okay, I'm way out of time. So we can also change some of the backgrounds, so we can have different backgrounds like satellite imagery. We can also take a 2D layer and drape it over a 3D model. So I've taken the Landcover classification and now I'm draping it over a 3D model to give a 3D effect. And that can be interesting if you're looking at movements of animal diseases as an example. The software provides the ability to share and print data, and we also have the ability to create a story so that you can take snapshots and then share them with someone else, and they'll see a sort of a kind of interactive PowerPoint where you continue to interact with the data of the story that somebody created. I'll skip this in the interest of time. So we have many different, most of the data is in what we call the data catalog. So the data catalog is the place where you can go and document your data. There are about 2 million layers in there at the moment from many different users and organizations. And it includes a search facility so we can look for evapotranspiration, and it's supported by the ISO metadata standard. It's built on CCAN, which is a very popular open source metadata catalog. A couple of examples where else we're using it. So water accounting, a subset just for water accounting for that community, agricultural stress index, early warning for animal diseases, livestock emissions, more kinds of livestock. We have a new soil database. We have one that's out already and a new one that will be coming out towards the end of 2024. We have a climate risk toolbox, which allows you to take your area of interest and do due diligence that you've looked at different climate change scenarios by generating a report to attach to your proposal. I think I'm more or less out of time. I'll talk just one little bit about the different kinds of data we support. So we've learned about the data being multidimensional in a cube. We also talked about tabular and geographic. Another way we distinguish data is between a data that's one-off piece of work published by someone and a piece of data that is supported by a data engineering pipeline that keeps that data up to date and constantly either grabs the data or processes the data. I think I'm more or less out of time. We have a set of tools that back up all of this processing. So this is our raster data manager. So it's able to process many hundreds of thousands of tiles, and it constantly keeps many of our data sets up to date. The analysis 2 function that we saw earlier also works with Google Earth Engine. In fact, many of the layers can also be sourced from Google Earth Engine. And we can automatically schedule data to be calculated. So if, for example, you're looking to keep an up-to-date statistical data set of the rainfall patterns in a particular set of districts, this will daily, 5 daily, monthly, calculate the figures and make them available as a tabular data set. Okay, so I'm out of time, a bit over time, my apologies. Yeah, I guess I can open the floor to questions.
We do have one online.
I can read the question that's online. This is from Drew Wheaton with Tetra Tech. So his question is, during the field validation and assessment step of the hand-in-hand process, does the team undertake KLL or KIIs with other relevant actors or private sector, civil society, et cetera, to understand why something such as rice storage infrastructure might not have already been developed in specific high potential locations? I wonder if there's a qualitative input that may not be captured in the data analysis and may help to explain the status quo in a given location.
Thank you very much for the question. So as part of the initial analysis stage, we have a team of economists that look actually at the current situation in the country and the opportunities. So making sure that it is viable, there is a market that can be invested in. So right from the very beginning, the economists are involved. So it's not only the data analysis. I actually focused in this presentation on the geospatial and the data analysis rather than on some of the economic modeling that's also done. So that's how we assure that rice storage locations are an appropriate thing to be following within the country. It's also conducted together with government. So they themselves are driving this process. In fact, they're the ones that select in the first place rice as an area they would like to expand in before we do the economic analysis. In terms of the locations, that is actually undertaken by government directly. So there is an interactive process where we are identifying the locations. Clearly, if you're sat at a computer doing GIS remote sensing and whatever, you need some kind of sanity and reality check that requires very local knowledge and to actually visit those locations. That is undertaken directly by the government counterparts before we come out with a list of detailed locations that would be attached to the investment proposal. Well, so what I'm talking about, that there are many other different kinds of value chains. It could be fish ponds or fish ponds with solar panels or refrigeration units. I just chose that one rice example today.
We have 5 minutes left. Go ahead.
Could you just say a little bit about the data kind of management and security for uploaded files? For example, if I have a file that has the locations of survey sites that I'm interested in joining to them, but those sites are protected by an IRB or some other kind of restrictions, what happens to the data once I upload it to this?
So for the data, we have various levels of protection. So the data is owned by what we call an organization. An organization has a list of members. Those members are able to see the private and the public data. The organizational administrator can then decide on what data they would like to be to make public. So it's possible to set up a closed organization. In fact, we have several cases where only the strict members of that organization have the access to that data set. Similarly, in the raster manager system, when you set up what we call a workspace, which is analogous to an organization, we put access rights directly on the buckets. So in this case, all the data is generated in cloud-optimized GeoTIFF with a stack file that accompanies it for Python programmers. But you won't have access to it if it's not a public bucket unless you've been shared that permission. So for example, some of the models that look at the disease risk, those data sets are on protected buckets and you would not get access unless you're a member of that group.
Anyone else? There's no more online, so 3 minutes. We can fit one more question.
Hi. I have a question regarding the point data that you mentioned. And going back to the disease outbreak. So when you use that feature, is it clear that data is coming from a granular level, or is it, like aggregated at admin and then you pick the admin?
So every data set, we consult the owner who decides the best way to show their data. And it also comes a little bit back to this privacy issue. They decide which data can be shown to which groups. The data set that I showed today for Empress I, for animal disease, is the finest grain level of data that is publicly available. So it doesn't contain confidential information, only public information. When we set up the data engineering pipelines to ensure that the data continues to flow, oftentimes we will also put a aggregate function or a calculation in to take two different variables and calculate a third variable. So, for example, we might be looking at a roll-up monthly, weekly, annually, and that can often be used to hide detail when somebody doesn't want to publish the full detail of the data on the platform to the public. So, yeah, it really depends on the data owner. Every data set has different requirements.
Okay. So on that, we can figure out if whether it's coming from aggregation or is it that the exact point that's what data is showing us?
So each of the data sets includes a metadata record that explains the process, how the data is collected, where it's come from. So you'd have to look at the metadata to understand that. In the case of the animal health data we saw, it is the actual best quality location that we have that we can share publicly. So yeah, I mean, it's the same data that goes into the animal disease hotspots, as an example, are calculated using this. It's also input into the machine learning models that we're using for prediction.
Thank you.